All right, this is the 12A problem 11 from the 2021 AMC 12. I keep getting asked in the comments about my score prediction or cutoff prediction. You can see that in the 1 through 5 video description. Okay, a laser is placed at the point 3,5. The laser beam travels in a straight line. Larry wants the beam to hit and bounce off. Okay, at this point, you don't know what they're doing anymore. Just draw a picture so you can understand what you're saying. So you're at 3,5. 1, 2, 3. 1, 2, 3, 4, 5. Okay, so you're right here. All right, so he's going to shoot it. He wants to hit it and bounce it off the y-axis. And then, so it's going to go something like this, right? And then down here. And then what? Bounce off the x-axis, then hit the point. So somehow it's going to come back 4, 5, 6, 7, 5. It's going to come back and hit here, something like that. You could do it by parts, but I don't know. Have you ever thought about how that laser beam's going to reflect? Right? Like in a mirror kind of thing. Its path going this way, if it didn't reflect, wherever it goes, whether you aimed it here and down there, anything like that, all such paths, you could have just kept going straight and you'd be at an equivalent point over here. And the distance from this point of reflection, I wish I had my zoom on right now, I could just erase this line in one shot for the other alternate path. This point of reflection, the distance from it to the x-axis here and the x-axis where it actually reflects, that's going to be equal, right? Because it's going to have the same angle made with the y-axis here and here. And furthermore, once it goes this way, same thing would happen with the x-axis. You could come down here, but that means we could have also just come straight over here. And so that doesn't look very good. It's not very straight looking, is it? All right, so we'll say it comes like this, right? Something like that. But anyways, then it would end up at basically -7, -5. And that distance from here to here is the exact same distance it would be if it went like this, and like this. And I got this idea from, they had them on old AMCs where you'd have like a cube or something, or a tetrahedron maybe even, and some fly would be trying to travel from this part of the box to this part of the box or something, and it wanted to know the shortest possible path. And the trick was to unravel it flat and just draw a straight line basically. I forget what the problem was. You guys probably know. If you remember what it was and you can find it and put it in the comments for others, that would be great. But they also had like a tetrahedron one too. And basically you just take the 3D image and fold it flat and just travel on the straight path. And that's what made me think of this. It's going to reflect. This is the same distance here. All you're doing now is distance formula. From 3,5 to -7, -5. So if you inferred that pretty quickly, man, this problem's pretty trivial for number 11. And if you didn't think of it, it happens next time, right? Okay, as I watch the videos, we're all trying to learn. We're all trying to improve. So 5 minus -5 squared plus 3 minus negative, this is 10 squared. 3 minus -7 is also 10 squared, and you would square root that. So it's going to be 2 times 100 in a square root, 10 root 2. You should know distance formula. You're doing the AMC 12, you don't know distance formula, you better know the distance formula. Just for those of you who might not know, who aren't familiar with the test though, I will write it down. It's the difference in the x coordinate squared plus the difference in the y coordinate squared. Okay, that's it for this one. We're on to number 12. Be right back. And here we go on the 2021 AMC 10A problem 14, also the 12A problem 12. All the roots of polynomial, looks like this, are positive integers, possibly repeated, possibly, right? We know what that means, definitely repeated, most likely. What is the value of b, this coefficient right here? Now the first thing is I don't like z, I don't like s either. I usually change those variables to x most of the time. So that's what I'm going to do here. But what I want to think about first is these roots. Polynomials to 6th degree have 6 roots. They could be repeated still, but they still have 6 roots, right? So then what are we looking at? Why do they give us this one and this one, but all the rest are variables? Well, probably because you're supposed to use Vieta's formulas. And this is the coefficient that you need to get the sum of the roots. The sum of the roots for every polynomial is always the negative second coefficient over the first. So we know R1 plus R2 plus R3 plus R4 plus R5 plus R6 is equal to 10. And what about this one down here? Well, that's how you get the product of the roots. The product of the roots is always this, the constant, over the leading coefficient. If it's an even degreed polynomial, it will be just that number over this, meaning it's 16 over 1. If it's an odd degree polynomial, like say it had been z to the 5th, then it would be the negative version of this over 1. Look up Vieta's formulas to learn more about those. There are a few more powerful tools in there, especially for cubics, like pairwise product of roots and stuff like that. So R1 plus all this, we also know R1 times R2 times R3 times R4 times R5, and finally R6 is 16. Now I happen to know 16 is 2 to the 4th. I also know we've got a lot of positive integers that have to add up to 10. So probably, if it's going to work out, there's probably a lot of 2's in here, right? So it'd be 2, 2, 2, 2. What would we have left? They'd have to be 1's, wouldn't they? Let's see. 1, 1, 2, 2, 2, and 2. Would these add up to 10? Well, I'll let you check. 8 plus 2 is 10. They definitely do, so these are the roots. So we now know we can write this. Again, I'm changing to x for my own reasons. And then x minus 2 to the 4th. That's what this polynomial represents. And so we want to know what the b value is. Well, the b value is the coefficient of z cubed. We could expand all this using binomial expansion, but maybe there's a faster way. Why are these both even? Maybe so that you can take out a power of 2, and then it would look like this. And this would be a cubic, and maybe we could think about it faster if we just attacked this. So x squared minus 4x plus 4 times x minus 1. We're going to just ignore the squared for right now. Distribute this x to everything. X cubed minus 4x squared plus 4x. Now distribute the negative 1. Line up your terms. Negative 1 times negative 4 is positive 4x, and then minus 4. So that expression, once gathered like terms or combined like terms, is x cubed minus 5x squared plus 8x minus 4, and then this is all being squared. And this generates that. Obviously the x's convert to z's, as we talked about. So I want the coefficient of the x cubed term. We could expand it. You could do that if you want. If you did it on your paper, that's fine. But I'm just going to think about how x cubes get created. I'm going to have to multiply this with one of these terms. It's not that one, it's that one. So I'm going to definitely get a negative 4x cubed because it's 2 of these side by side, right? So I'm multiplying this times all 4 of these, but the ones that create the x cubes are the x cubed in this one. Then when I distribute this term, right, because again, it's 2 of these side by side. So now you're distributing this negative 5x squared to all of those, right? And so if you multiply it, again, which one would it have to multiply with? It'd have to multiply with this one, and that's going to give you your negative 40x cubed. Furthermore, when we get to this one, it will have to go with that one, which is also going to be negative 40x cubed. And then when we get to this one, it will have to multiply. So you're basically at the end of this term, multiplying it with the first one here to get another negative 4x cubed, negative 88. Answer choice A. Let's get on with it. All right, we are on to the 2021 AMC 12A problem 13. Of the following complex number z, which one has the property that z to the 5th, and that right about there you should be thinking of a particular theorem, right? And so what theorem is it? It's that dead guy's theorem. And we say that dead guy's theorem because nobody knows how to say his name correctly. Actually, I just looked it up. It's Demoivre. I think, something like that. I'm not French, and he was French, but he's also dead, and I don't think he cares if we mispronounce his name. Most of the time I try to get the names right, but come on, it's a hard one to say. Unless you're a French person, that's probably easy. Cool, but there is a mispronunciation on YouTube, by the way. It was like Demoivre or something like that. And, what? How did they even have that? How does that happen? Famous guy. Sacred. Okay. This theorem, how does it work? Basically, you're going to have a complex number written in polar form. So that would usually be written r cos of theta plus I sine of theta. But that, in fact, often gets shortened to just r cis theta. If you haven't learned that notation, you should, because time savings. It adds up over your life. You could, have an extra 5 minutes by the time you're 70 or something. And then it's, I don't know. All right. Anyways, take it to a power now. So it's if this is true, then what? You would have z to the nth power is going to be r to the nth cis n theta. Okay? So we're just going to walk back over here. We want to know which one has the property that z to the fifth has the greatest real part. So all we're going to do is convert all of these. The real axis is here, the imaginary axis is here, -2 is over here at 180 degrees. And so A is going to be 2 cis 180. If you want to write in radians, go ahead. Oh, yeah. So radians, so much cooler, right? No, I like degrees, thanks. I mean, we can do radians, but, the more sophisticated people do radians. But here we go. So -√3 plus I, that's going to be going over here about √3, which is about 1.7, right? And then you're going to go up 1, and you'd be about right here. So what does that mean? We've got a right triangle here, and you're going over √3 and up 1. Doesn't quite look like this. This would be 30 degrees, okay? And then that would mean the angle that creates it with the positive x-axis is 150. And the radius would be 2 by Pythagorean, 2 cis 150. All right, C, what's it going to be? You should recognize with the √2's that it's going to be a 45-degree angle. It will be in the second quadrant because you're going over √2, up √2 here. That'll be 135 degrees, and because they're both √2, you multiply by √2 to get 2. It looks like all of these have the same radius. So 2 cis 135. D, -1 plus √3i. Where is that? We're still in the second quadrant. You're over at -1. You're up at √3. So it would look like this. This is √3. This is 1. Yeah, whatever. Negatives. This is 60 degrees, making the angle 120. So it's going to be 2 cis 120. And then you have 2i, which is going straight where? Up. Straight up to, it'd be 90 degrees. And so that would be 2 cis 90. Now, none of these 2's are going to be terribly impacted by taking it to the fifth power. They all become 32. So we really just care which one is the farthest this direction angle-wise, right? 180 times 5, because you're multiplying by 5 right here, going to the fifth power, is going to be 900. Where is 900? It's 2 revolutions, and then, so 720 is 2 revolutions, and then 180 more. You're facing over here, basically. Like, you're facing this way. That's not going to have a high real part, because your real axis is like the x-axis. You want a big positive x value there. You're not going to get it with that one. 150 times 5 is 750. As we said, 720 is 2 revolutions. You're going to go up 30 degrees, which is not bad. That's pretty good. For the x value of these graphs, right, that's going to be the cosine value, which is where you're getting that. Yeah, so the cosine value will be farthest this way, right? And so cos of 30, since Cos of 0 is 1. The closer your angle is to that x-axis, the farther your x value is going to be. Okay. 135. 135 times 5. 5 times 13 is 65. Put a 0 on the end because it's really 130. You're at 5 times 130 is 650. And then you'll do 5 times 5 is 25, but you'll put at 675. Basically 650 plus 25. Okay, you're not quite to 720 with this. How far away are you? Well, 25 to 720 more after that. It's a 45-degree angle in quadrant 3. But again, the x value at 45 degrees is not going to be as far to the right, far positive as it would for 30 degrees. So this one's not it. This one's not it. It's probably this one here. Cis 120 times 5 is going to be 600. Again, that's going to be 120 degrees short of 2 revolutions. So you'll be somewhere over here where the x values are negative, which is how you'll feel if you choose that answer. 2 cis 90. 90 times 5 is 450. 450 is going to be a quadrantal angle, 360, it's going straight up at 90. Your x value there is 0. Very satisfied now. It's going to be B, which was negative root 3 plus I. If you don't know this theorem, they do like to use it on the test I've seen. It's probably come up like 6 times. It's something you probably want to add to your arsenal over the next year if you haven't learned it yet, or before the B test if you have time. All right, see you guys in the next problem. All right, this is the final problem of this set for the rapid fire for the AMC 12. I'm not going to do the 15, mostly because when I did it, I had to do a casework bash that took a long time. I sensed that there's definitely some underlying advanced counting principle technique. I did take a glance at the forums and somebody mentioned something called Vandermon's identity. Be honest, I haven't taught that one to myself yet. It is probably something we should all be learning. So because I can't explain that one at a high level, I decided to put it off until I can, because I don't want to waste your guys' time when you could be learning that method from somebody who can explain it better at this time. And I don't think the casework one is really worth explaining. I'm sure you probably all encountered trying to do all those cases. There's a lot. So it just took a long time, and I don't think it's not beautiful or efficient. So I'd rather wait until I can master the techniques that are really needed to do that problem as quickly and efficiently as possible before I try and explain it. But let's do this one here, the 2021 AMC 12A problem 14. What is the value of, that's what that looks like, right? So you're kind of like sigmas, and that one's to 100, and this is logarithms, and the base is to the, oh my gosh. Okay, well, don't panic. That's the secret, right? We talked about this before. Let's just break it down. Let's just focus on this one. What's going to happen? We can take this k squared, and it's an exponent of the 3. We could pull it in front. So ignore the sigma for right now. Just pretend it's not there, right? K squared times, and I'm going to go ahead and convert this to a different base. Base 10, let's just do it in. Doesn't really matter. There's not really a benefit to any other base. So I'll have log of 3 over log base, or log of 5 to the k. So if you don't know change of base formula, it basically looks like this. Log base a of c, you can make the c go up, the a go down, and what I mean by that is I choose any base I want. The c went to the top, the a actually goes down here. You should know this one from pre-cal, maybe algebra 2. It's pretty common, and it does come up a lot in the competitions. Change of base formula. So moving back over to here, now we have an exponent on the log again. So we can pull that out front just like we did the k squared originally. So this k will come out here. Now it cancels with the squared. Okay, we're getting somewhere. We've got log base 3 of 5 times k. That's a constant. It can come outside the sigma. You're then going to have log of 3 over log of 5 times the summation from 1 to 20 of all the integers. So that's going to be 1 plus 2 plus ... plus 20. Okay, great. Now, what about over here? This is a times in the middle. You're not adding. Let's get to breaking this one down. We're going to have the k come in front, and you should be able to see it right now. You can see it, right? You saw what happened with this. You saw how that k came out. This k is going to come out too. You're going to get k times log of 25 to the k over log of 9 to the k. Wait. Yeah, that's right, sure. And then the k's will actually come in front. So this k I could have pulled out from the front from the very beginning. It's not there anymore, actually. I did that already. It's right here. This k came in front, so it's not there. So now when this k pops out in front, it's going to what? It's going to cancel with this k, right? So this k will come out in front. The exponent on a logarithm can go in front of the log. It's one of the log rules you learn, one of the first ones you learn. So now it will cancel here. So really this expression doesn't even have any k's in it anymore. You basically have 100 of these being summed up, but is there something more? These look like they might play well together. Why is this 5 squared? Why is this 3 squared? Well, probably because we're supposed to change its appearance. If I now make this log of 5 squared over log of 3 squared, those 2's come in front and cancel. And so we don't need them anymore. It's actually, it looks like the reciprocal of this. And how many of these are we going to have? We're going to have 100 of them. So it's going to be times 100 of the log of 5 over log 3 expressions, right? So log 5, let's make that 3 a little bit nicer. Log 5 over log 3. Because you add, it's like x plus x plus x plus x 100 times, you have 100x. Well, our x is this weird log expression, right? So everything's being multiplied. These are reciprocals. See ya, they're gone. All this complicated stuff, it's just 1 to 20 times 100. So the 1 to 20 is the n times n plus 1 over 2. You get 20 times 21 over 2, drop the 2 into here to get 10. 21 times 10 is 210. Toss 2 more zeros on the end of that. You are at 21,000. Answer choice E. Why 2 more zeros? Because we're times 100, right? That's it for this one, guys. I don't think I'm going to have any more time to film today for AMC 12 or AMC 10. I got to work now. That's the way things go. See you guys in the next video.